All right, today we're gonna do Bernoulli's equation. We're doing a 550 in the textbook. So the first thing you gotta write for Bernoulli's equation is you gotta simplify it into one side equals the other side. So for this case, we have point A, which is here, and then we have point B, which is here. So we're looking for, in this scenario, we're looking for the pressure at B, which is this right here. And we are given our velocity at A, which is this term. And we're also given the pressure at A, which is this term. So in this scenario, we are given that air is our fluid. So we're just gonna write this straight through. So it'll be 1.8 kPa times, which is specific weight, and it says asking for our density. Our density would be 1.2 because it is air at 20 degrees Celsius, which is important because the temperature changes the density of air. So we have 1.2 and we're using SI units, so our gravity constant is going to be 9.81, and that'll give us our specific weight plus b squared, which was 8 meters per second, which is given to us, to 9.81 plus height. All right, so this is very important. In pipes, when you have pipes like these right here, the height is going to be the same because they're both going to be acting at the datum area of the pipe, which is basically the middle of the pipe. So we can cancel these out. So we only have to worry about the pressure, velocity, gravity, and specific weight. So in this case, we have PB, which is this plus B squared 2G plus 0. And we have to find our V squared before we could solve the rest because we're missing, that's the only thing we're missing. But since we know this is a pipe, you're allowed to use the conservation of mass theory to solve for that VB so you could solve for the rest of the Bernoulli's equation. So we'll do this, which is MA dot equals MB dot. And it'll be very easy to solve if we actually just do, what is the thing again? What's the formula? All right, just give me 1 sec. I believe the formula is PQA, which equals PQA. That's not right. PVA, which equals PVA. So again, our density is 1.2, 8, and the area which will change. And in these pipes, these areas are, what's it called? Circular. So we're gonna use the area of a circle, which is pi r squared. And they actually gave us the diameters, and that's how you know it's a hint in this problem that you have to solve for VB or VA to manipulate the equation to solve for one of the pressures in this scenario. So it would be pi half that 200 times 10 to the negative 3, because watch out for units, which equals 1.2 BB, since it's our missing, pi 100 times 10 to the negative 3 again, and watch out for units. And don't worry, at the end I'm gonna put all the steps how to solve, and I'll be right back. All right, I'm back. Let me tweak the camera a little bit to see so you can see what I did for my work. I used the conservation of mass theory, which is basically right here, and it's in my previous video. Basically, mass in equals mass out, and I got VB equals 32. You'll know that you're doing it right when you have a smaller area and you'll get a way bigger velocity. That's actually one of the keys that you know you're doing it right, and I stated that in my previous video. But as of right now, now that I have my VB, I can solve for the rest of the Bernoulli's equation. Whoops, it should be an equal sign here. and solve for the pressure at that point B. What I did right now is I'm just doing a bunch of algebra so I can just solve it straight through so I could save our time. All right, I'm back. I got pressure B equals 101.224 kilopascals. All right, this is also very important. I actually messed up on this. When you're doing pressure, make sure when you get a kPa, it's supposed to be in PA because watch out for those units or you're gonna get a completely wrong answer. So for this equation, I would do 101.8 times 10 to the third divided by that. So there's a couple more things I'd like to go over for this problem. So when you have pipes like this and you're doing Bernoulli's equation, V1 is going to be lower than V2. And it's going to look more like this. Like pressure 1 is going to be higher, velocity 1 is going to be lower, and equals pressure 2 is going to be this, V2. So basically, these pipes' purpose is to increase the speed while decreasing pressure. And again, sorry for the handwriting. And let me, I'm not sure if you can see that. Yeah, this right here. And here are the 3 steps for Bernoulli's. So you're going from 1 to 2 in pipes, or in case you have area. Finesse, M in equals M out for missing velocity. In this case, which we did, we had to finesse the equation so we can solve for that velocity and backtrack back into our Bernoulli's equation and solve for our pressure. And also, just in pipes, Z1 equals Z2, so they're not important. And sometimes in Bernoulli's equation, you will go from, say, here 2 to 1 right here. In this part, P1 would be 0 since it's at the top of the water. And P2 would have a pressure. And also V1 will be 0 because it's at the top of the water, and typically in fluids in this class, when you have water and you're at the very top, the velocity and the pressure is going to be 0. So typically you're going to be solving something like, if you were going to like 1 to 2, you know, you do your average Bernoulli setup, which is this. And this whole half would be 0 because you can just take that datum point, Z, and just use it there. So you would take this as a reference point as 0, like, and this would just be your Z, your delta change. So this whole spot, only when you're at starting from the top of the water to the middle of somewhere else, you would start like that first half, which is the top of the water, to be 0. And this concludes the Bernoulli's equation. I'm gonna be making more videos shortly, and that's it.